Hey, all you derivative devotees, we are back and we're talking about applying the power rule we learned yesterday. And just to answer some of those same questions, but now we can get to them in a bit snappier fashion here. So, classic one right here, y equals negative 1 over x squared, the rational function. VA at x equals 0, HA at y equals 0. Writing the equation of the tangent line at x equals negative 3. So here is that point, negative 3, right there that you're talking about. And the tangent line would be something right there. It looks like it's pretty flat, but definitely with a negative slope. And keep in mind, to write the equation of a line, I don't care which form you use, but you need two things really. You need the point and the slope. So that point of tangency is at negative 3, but you got to get the y coordinate. So using this notation, y of negative 3, you're plugging it into here. Anytime you do a plug-in, you try to show where you plugged it. And negative 3 squared is 9. So, hey, there's our y coordinate. Negative 3, negative 1/9, which seems to be about right for that y coordinate. And the slope is, of course, from the derivative. So here we go. Our slope. And remember, to use the power rule, we want to rewrite this in that power rule format. So negative 1 x to the negative 2, right? Bringing that up top so it's something times x to some power. And then our derivative is negative 2 times negative 1, which is positive 2, x to the negative 3. Or if we write that with a positive exponent, 2 over x cubed. And now to find the slope at that point of negative 3, remember that's what the derivative is for. It will give you the slope at any x value on this curve. So y prime of negative 3, plugging negative 3 into here, and that will give you 2 over negative negative 3 cubed is negative 27. So negative 2/27. There is your slope. And so you got the slope, you got the point. Sounds like a good time for point slope form to me. Y minus negative 1/9 is y plus 1/9 equals the slope of negative 2/27 times x minus negative 3 or x plus 3. And there you go. If you want to do it in any other form, be my guest. But there we go. Very nice, right? Okay. Now here's a classic application of the derivatives, and you'll do some word problems with this also. But finding any points where this graph has a horizontal tangent line. So hopefully you can visualize where that might be, right? Anywhere here would have a positive slope. Anywhere here it would have a negative slope. Where is it have a horizontal tangent line, or in other words, a slope of 0, would be right here. There's one, and there's another spot right here where the graph is flat for a second. So what we're really saying when we talk about tangent lines and derivatives, that's derivatives give you slope. So horizontal tangent line has a slope of 0. So you're really asking, when does the derivative, for what x value does f prime give you a slope of 0? When is f prime equal to 0, right? Since that output of the derivative is always that slope on the curve, like in this problem. So here's the first step. Let's find that derivative. And this is where the power rules are so nice. Just power right through this, right? So you get 3x squared. F prime x equals 3x squared minus 12x minus 36. And now I'm asking where, for what x values, does this equal 0, right? And that's what you're doing. You're solving a little quadratic. Notice it's going to have two solutions here. One right there, one right there. Graph provided for you. And factor out that greatest common factor of 3. Then this actually factors further, so we don't have to use the quadratic formula or completing the square or any of that stuff unless you want to. That will be minus 6 plus 2. So our two solutions are at x equals positive 6 and x equals negative 2. Which, of course, you may have been able to tell on the graph here, but that would be assuming that x scale was 1. I did provide it just so you can visualize that that's what happens, right? You're talking about this spot and this spot. However, notice the direction said find any points. Find any points, meaning coordinates, ordered pairs. So we need to find that y value at 6 and that y value at -2. Where do we get the y values on f of x? From the f of x equation. So we're doing a couple plugins here, but into the f equation, show that plugin. F of -2 gives you -2 cubed is -8, -2 squared is 4, times -6 is -24, -2 times -36 is +72, and +4. If you want to use a calculator, be my guest, but this is 76 minus 24 is 52. 52 minus 8 is 44. So yes, that y coordinate is 44. So the y scale here was definitely not the same as the x scale. So hopefully you didn't assume that. And that means this y value here should be something really, really small. So f of +6, 6 cubed, 216, minus 6 times 6 squared will just be 6 cubed again, 216, minus 36 times 6, minus 216, plus 4. So those cancel. -216 plus 4 is -212. So your coordinates are 6, -212. And that's pretty cool because in terms of graphing polynomials, think about what you now can do. You put in you know how to find x-intercepts, from Algebra 1 and y-intercepts, you know about end behavior. And now you can find exactly where a graph turns around and how high or how low it was when it did so. So I mean that's pretty powerful stuff when you start to apply this to word problems like, values of stocks. When is it going to be at a maximum? When is it going to be at a minimum? And how low will it be? And those kinds of things. That's a big part of what calculus is about. Using these rates of change to determine when things are going to max or min. Okay. And of course, let's just talk about a couple more here. So we've got this right here, this graph of f of x equals x to the 2/3. I don't know if this is a shape you would be automatically familiar with, but just so you kind of know where this shape comes from, if you think of it like the cube root of x squared, and you know or should know what the cube root of x looks like, it looks like this. It was like that x cubed graph, but sideways, right? It's the inverse of it. And that's cube root of x. Cube root of x squared is very similar on the right side, meaning when you plug in positive values, the square won't really impact that, and you take the cube root of it. But when you plug in negative x values, the big difference is you'd be squaring them, making them positive before you take the cube root. So you really get when you do this, you kind of take this part and flip it up, and now you get positive y values along with these already positive y values, which is why you get this kind of seagull shape here. So the domain of f of x is what I'm asking for here. You have the graph, you have the equation, more importantly, to know that domain, you're looking for when things are undefined or imaginary, and because it's cube root, this is never imaginary, and there's nothing that will make it undefined. So the domain is all real numbers or -infinity to infinity if you're answering in interval notation. And you can see here, hey, it's defined everywhere. There's no holes or VAs or anything like that. F prime of x. Well, if f of x is x to the 2/3, then f prime of x, use our power rule, we get 2/3 x to the -1/3 when you subtract 1 from that exponent, which gives you this. Remember, I don't like to leave negative exponents, so you move that to the bottom. And there's your derivative equation, or you could make that the cube root if you prefer. And now I'm asking you about the domain of f prime. The domain of f prime, well, you look at this equation, it's still cube root, so you're never going to get any imaginary, so it's not like x has to be positive or anything like that. But now x is in the denominator, And the one thing you can't have is a denominator that equals 0 because that's undefined. So the one thing you can't have for x is only one single value. X can't be 0. Or, again, interval notation would be like this, right? And I would just like to make that point of, well, what's so special about 0 that the derivative does not exist even though the graph exists? So take a look at 0. That's right here. And if you think about what the derivative represents, what it gives you the slope or the change of the curve at any moment, the instantaneous slope at any given moment. And of course, any point you pick, clearly has a slope. It's clearly decreasing over here. It's clearly increasing over here. So it's got negative slope on the left. It's got positive slope on the right. But right at this point, at x equals 0, it's an abrupt change. It just instantaneously switches from this to this. There's no smooth change like in a polynomial. So that's something you're going to explore next year, and what they call a cusp, a sharp point on a graph where it doesn't have a rate of change at that moment. And at a cusp, the derivative does not exist. Not something you need to know for a fact right now, but it's a nice little exploration between algebraically what you're getting here and what that represents here. And that's what we're continuing to do, is just build that understanding of what the derivative is. I know you know how to get it with the power rule now. That's great. But can you apply it? Do you understand what it represents? So to further, bring that understanding home, I've got this graph here. There's no algebra involved. This is a graph of f of x, and we've got a bunch of highlighted points, a through h. And of these points, which, if any, have these properties? So this kind of will tie these two things together. Keep in mind this graph is f of x that you're looking at. So f of x is this graph, and f prime of x represents the slope on this graph. So is there any of these points where f of x is greater than 0 and f prime is equal to 0? So f of x, when we talk about f of x, we're talking about the y values on this graph. So the y being greater than 0 would just mean I'm above the x-axis. So I got a bunch of points that are above the x-axis here, a, f, g. Are there any where the slope, where f prime equals 0? And so picture those tangent lines, and hopefully you land on that point pretty fast. A slope of 0 means it's got to be flat at that 1 split second. And so that would be point G, where both of those things are true. Part B, f of x equals 0. So again, you're saying, is the y value 0? And that would be either right on the x-axis of B or E. But f prime is less than 0, so the slope at that moment is negative. And that would be right here. Picture those two spots. If you draw the tangent line there, that's got a negative slope, that's got a positive slope. So we are talking about B is the only place where both of these are true. F of x is less than 0, so again that means your y coordinate is less than 0, so you're underneath the x-axis. So that would be C, D, H. And f prime is greater than 0. So y coordinate is negative, slope is positive. Slope right there, positive. Slope right there, negative. Slope right there, 0. So the only place where both of these things are true, point D. And lastly, the f of x is less than 0, so the y coordinate is negative, and f prime is less than 0. So y coordinate is negative, slope is negative. So again, we're back to these points, and which one had a negative slope? H. And there we go, and that's the only point where both of those things were true. So nice mix of algebra and understanding, hopefully, on today's worksheet. Hopefully you're getting these things. If not, just please ask questions and we'll get it straightened out. Have a good day, kids, and good luck.